easy. Then we'll start with where we left off in 6.3. We did look at the example here of, this one was we derived the area of a sphere using the general slicing method. And that's where we find a volume by integrating the area function. Anyone have any questions on this? This directly builds into our two main methods of finding volumes for solids that get rotated. Everybody cool with this? All right. So what we're going to look at then is volumes of rotation here in the remainder of 6.3 and all of 6.4. And so what we're looking at is, finding the volume of this gold figure, but thinking about it from the perspective of we're only concerning ourselves with what's the area of, so like when we integrate area times dx, we get a volume. What the area function we're concerned with was the area of what? The cross sections, right? The cross sections were simply what kind of shape do you make when you slice through your region? Okay. So the only time we want to think about the volume as a whole is initially in trying to, just to see where this comes from. But again, what we're going to do is we're going to take this region here, and it's generated by taking R, capital R, and revolving it around the x-axis. So we've got to think that if we have a cross section or our slice or our rectangle in here, and we're summing up infinitely many of those, what happens? What shape does the rectangle take when we revolve it around the x-axis? That way we'll only focus on that shape because we're concerned with that shape's area. Does that make sense? And so hopefully you can sort of visualize this in your head, but when we slice perpendicular to the axis of revolution and we revolve that around, what we generate is a disk or a circle. They just call them a disk for now. So that's where the formula comes from. We're focusing on the volume of this disk that's generated, or sorry, the area rather, and the area is pi r squared, with the distance from top to bottom being the radius of each one of those disks. And so this thing here would give us this disk. There's our radius. We would have another cross section here, giving us that disk with this radius, right? So the radius in this instance varies, and the radius is determined by the elements running this way are always determined by the top minus the bottom. Here it's just the function minus 0. So the radius in all of these instances would be just determined by f of x minus 0. Okay. So that's the top minus the bottom. For this distance, this is our radius. So then we have the area of each disk or circle as pi r squared, which is pi times f of x times your function squared. So we see that here. This is our area function here. That's a of x. So that formula is specific to the disk method. And so if it says find the volume of a solid by revolving this around a certain axis using the disk method, then yeah, you've got to remember this formula. If you're going to use the disk method, it has to be pi f of x squared. Does anyone have any questions on this initially? All right then. So let R be the region bound by e to the negative x here in red. Y equals to 0, x equals 0, and x equals ln of 4. So remember, the region we're concerned with does share all of those boundaries as part of its sides, if you will. So we have this here, that's our ln of 4. X equals 0, y equals 0. So this is our region, capital R. All right, and then what we want to do is we want to use the disk method to find the volume of the solid generated when R, this region, is revolved about the x-axis. Just sort of extend this here. And I usually will draw this just so we can remember that we're revolving it around the x-axis. So what would the volume look like? Anyone want to take a shot at it?
You take the integral from 0 to, what's that, 1 point, what was the upper limit of integration?
This one right here?
ln4, yeah.
Yeah, that's ln4, right?
And then you run pi times the square root of, what was the function again? It's e to the minus
E to the negative x, right?
E to the negative x, so e to the, yeah, so e to the minus x squared is the same as e to the minus 2x, right?
Right.
dx.
dx. All right. How does that look? Remember the area, I'm going to erase a little bit of this. The area of this region, so I do want to back up right quick just to give you something to remember, because we do look at a different method. The disk method, notice that occurs whenever your slices are perpendicular to the axis of revolution, right? Like if I have this axis of revolution, perpendicular will give me a circle, or if this were my axis of revolution, rotating it like this would give me a circle, right? So the disks that you generate, that are generated, the disks are always perpendicular to the axis of revolution. So that's how you know how to slice it and how to integrate with respect to x or y, is the disk method. We'll just note here, I don't know, whatever you want to call these things. Slices, rectangles, whatever. Slices are perpendicular to the axis of revolution.
Perpendicular.
Huh?
Perpendicular.
Perpendicular. Yeah, that's a good way to remember it. Yeah. So yeah, it does matter. When we look at different methods, if it says rotated around this axis and you slice it perpendicular, it's going to always give you a disk method. So, and again, these things are important because they give us a bearing on how to start out the problem. Are we integrating with respect to x or y? The bounds in terms of x or y, it tells us all of that information. So then we're just going to draw one of our disks here. Since we're revolving it around the x-axis, the disk is perpendicular to that axis. So remember this has a thickness dx, so we're integrating with respect to x, ranging from 0 to the natural log of 4. So those are our bounds. And then we have pi times the radius squared. Okay, so that's our radius. Okay, any questions on the setup? Yeah.
But if it was like another function that was the bottom, would f of x minus g of x be squared?
Right. Well, no, not all of it. So we will look at the situation where it's kind of like what we saw in 6.2 with areas versus what we saw with regular Riemann sums, I guess. We can take a region like this and rotate it around the x-axis. It's really close. You wouldn't square the whole thing, though. We'll look at that in a minute. Okay, any other questions? I mean, as with most of these types of problems, the setup is the most crucial thing. Okay, so then we'll come down here. So we've got e to the negative 2x. What's the antiderivative of e to the negative 2x?
Negative e over 2 to the negative 2x.
negative 1/2 e to the negative 2x. Do you all agree?
Yes.
Evaluate that from 0 to ln4. And we have pi times all of this.
So hopefully you don't need to, but you could do a u substitution here. However you do those. Right, and then this becomes the integral of e to the u du. Just much more efficient if you just know those. The antiderivatives, especially of these functions with like a linear argument, it's much more efficient just to know those as opposed to going through a u substitution each time. All right. Okay, so we've got our pi. And I'm actually going to pull out our constant of negative 1/2 as well. I'm going to just take that out. You can carry it through both computations. I just prefer to take them out. So we have that. ln4n for x, we have e to the negative 2 times ln4 minus e to the 0. And we'll just leave the answer exact. Let's go over here. Minus pi over 2. What is the value for e to the negative 2 times ln4? E to the, close.
Because you're taking the 4 and you're doing it to the negative second power.
Right,
so
yeah.
1 over 16. Or you don't know e, so 1 over 16.
1 over 16. Yeah, 1 over 16. Minus 1. Yeah. Remember power rules here. Power rule for exponential or for logarithms. That's the same thing as e to the ln of 4 to the negative 2 power, which is e to the ln of 1 over 16, which is 1 over 16. So that's our, I mean, I guess that's our exact answer. I don't know if
Can't you simplify it more though? You can make it 16
Yeah.
over 16, and then that one's pretty easy to get all the way.
yeah, we could say 1/16 minus 15/16.
And then multiply by pi.
Yeah, multiply through. But yeah, so I mean, just a little bit more work to continue this, but does anybody have any questions on that? All right. Let's see what. All right, so I'll let you all try the next one. It's 15 pi over 32. 15 pi over 32. So let's do. Let's do 6 minutes for this one.
always get confused with the circles.
So you just need to be really careful with these. A lot of you are getting the right integral, but it was only going to give you half the volume. So I think it's always conducive to draw these things out just to get an idea of what you're actually dealing with. Now, this is a part of our circle, right? Because this is really x squared plus y squared equals to 25. So there's a circle radius 5, but it's the values for when x is positive. We start off here with this right here is our x equals root 25 minus y squared. We want to, and x equals to 0, of course, is this. So we want all of this. We're going to take this entire thing and rotate it around this axis. Now, we're rotating around the y-axis. If we're using disks, our disks have to be perpendicular to the axis of revolution. So all of our disks are going to look like this. Once we revolve them, we'll just focus on that one in particular. So that tells us that we have to integrate this with respect to y. And our y's actually range from -5 to +5, right? Those are the y values that give us to fill up that entire region. So we're going from the volume would be pi times the integral from -5 to 5. So pi times our radius. And our radius in this case, just like it was in all of the others, is just the right thing minus the left. So it's our function minus 0. So there's our radius, right minus left, r squared. dy actually makes that a lot easier for us. Or if you wanted to do that the other way, you could say this is equivalent to 2 pi times the integral from 0 to 5, r squared. So either one of those is correct. Is everyone clear on the differences? Like if you started off by going from 0 to 5, there's nothing wrong with that. But if you did go from 0 to 5, you're just finding the volume of this revolved over here too. So you would just be finding the without this 2, you'd be finding the. So if you were just like this, you're just finding the volume for the top half of that sphere. Anyone have any questions? All right, so then we'll just kind of write this out here. 2 pi. And so this just becomes power rule for antiderivative. So of course that's the I guess the long-winded way to get there. We could also verify is that actually correct by just using a formula for a sphere, right? So if we take this region here, revolve it around the y-axis, then it's going to generate a sphere of radius 5. So we can just check it that way if we need to. You see that it will be the same thing, 500 pi over 3. Any questions? Okay, so then we'll move into a similar but more generic example or situation rather. When our region isn't actually against the axis of revolution, Well, if you can see the kind of the figure that it generates there, you'll look at it here too. So here's my rectangle as I revolve that around the x-axis. We're just concerned with what shape it makes so we can find the area of that shape. So since it's not touching the axis, as we would expect, there's a gap. But what we're creating are these, it's a generic disc, right? They call them a washer. So it's the washer method here. Here too. So the area of that, and you know, I think the biggest point of confusion, maybe, or one of them, is the way people tend to set these up. So we'll just kind of exaggerate our washer there, our center, say somewhere in here. We're finding the area of this thing. Right? That's what's giving us this here, our washer, our outer radius here. Radius here. Right? So all of this stuff revolved around this axis gives us all of this stuff. Or all of this stuff. Yeah? So the way we compute the areas, we just compute the area of the larger circle minus the area of the smaller circle. So we'll just call this here our capital R for the larger radius, and this one here for for our smaller radius, lowercase r. That's where, if you've seen the formula already, that's where the formula comes from. The distance from the top function to the axis of revolution is what's giving us our outer radius or our larger radius. The distance from the bottom function to the axis of revolution is giving our smaller radius. Maybe I'll just erase the fact that we're calling the region capital R as well. We're now calling the larger radius capital R. So this area is equal to the area of the outer circle minus the area of the inner circle. So just keep this in mind, it's this setup, it's not pi times r minus pi times r quantity squared. It's both of those individually squared. So of course the capital R again is determined by this height from here to here, from top minus bottom. So the capital R is just simply f of x minus 0. Lowercase r is top minus bottom, g of x minus 0. That's where we get our formula here. Outer radius, pi times your outer radius squared minus pi times your inner radius squared. And that's going to give us our area function for integrating. Does that make sense? So it's each individual one times pi squared, not the whole thing squared.
What if you were to rotate around a different axis other than 0? Would you include the minus inside the square?
Yeah, we'll look at an example like that. So we'll look at an example of taking a region like this and then rotating it around an axis like x equals a -2 or something. Sorry, y equals a -2. But I think, you know, if we think about it this way, we can see what changes if this is the situation. And we'll look at that in a minute. I guess that's not expressed so from your textbook, so we'll just write it down. Volume.
integral from a to b, pi times f of x squared minus pi times g of x squared dx.
Or we could take the pi out, but you've got to remember with the washer method, it's always top function squared minus the bottom function squared. It's never the top minus the bottom squared. Or with respect to y, we could write that out too. The only thing that would change, of course, is how your rectangles are running. This would be like this here. So H and W in this situation, which function on the left or the right is H? The right. Yeah, because remember in this situation, when your rectangles are running this direction, it's the right minus the left. So this is our H function, H of y. And this is our W. But again, the way you know you're dealing with a washer, not a disk, is simply because the region we're bound by is not completely flush with the axis of revolution. So in that instance, we revolve this around the y-axis. Hopefully you can clearly see that there's going to be a space that's going to generate that sort of the hole in the washer, if you will. Does anyone have any questions here initially? Okay, so then we'll look at example. Let R be the region bound by, excuse me, y equals x plus 2, x equals 0, and x equals 4. It says use the washer method. The volume when this thing's revolved about the x-axis. So if you just want to remember the washer method, it is more general than the disk method. The disk is, again, just a special case of the washer, where that bottom function is 0, or is the axis itself. So let's just draw a quick sketch here. Here's y equals x. Y equals x plus 2. X equals to 0. Draw this in a different color. X equals to 0. And x equals to 4. So that's somewhere over here too. So again, maybe we don't want to draw this. We just want to think about the region that's shared by all of these. So it's this parallelogram that we're revolving around the x-axis. Now it says it's explicitly use the washer method or the disk method. It could say the disk method, so don't let that throw you off. It's not a disk, clearly, but our cross sections using the washer method revolved around this axis. They have to be perpendicular to the axis of revolution. So our cross sections come in through here like this. We're integrating this with respect to x. Let me just draw this a little bit larger here. Those are our cross sections. Write this here. This is x plus 2. So our volume then is pi times the integral. X is going to range from where to where? 0 to 4. X ranges from 0 to 4. What would the outer radius be? The larger radius?
X plus 2.
X plus 2. Does everybody agree? The outer radius is x plus 2. And that's just the longest distance from your function to the axis of revolution. So our outer radius squared we have to subtract off the inner radius squared, which is just x. Inner radius is x. It's actually, you know, I think it's more conducive to think about it. The inner radius is x here, but it's really, we want to think about it as x minus 0. Same thing with the outer radius. It's x plus 2 minus 0, because it is this distance. Here's our outer radius, the distance from here to our axis of revolution. So we just want to think in general terms, it's always top minus bottom. Our outer radius is top minus bottom. Our inner radius is also top minus bottom. So x minus the quantity x squared. I'll show you like this. X squared. So that's our setup. Pi times the outer radius squared minus pi times the inner radius squared. Anyone have any questions on that? So that's, I'm just going to expand that out, subtract the x squares. It ends up just being a linear function. So it's, just put the answer at 48. Anyone have any questions at this point? Just similar thing, we want to use it says use the washer method. Volume revolved about the y-axis. So if these are on your homework and the regions are already provided, I think that's all well and good. But I would try just sketching these out by hand before I looked at the computer. Because on the exam, you may be provided with the region already. You may not be. So you want to be familiar with both. Okay, so we have the line y equals x. Y equals 2x, and y equals 6. We'll just say the 6 is here. So it's this region we're looking at. I'll do these in different colors. Say that one's y equals 2x. Okay, so sketch your region and then go back to the problem, what am I using? I'm using the washer method revolved about the y-axis, and my washers need to be perpendicular to the axis of revolution. So then I'm going to draw my rectangle in the region perpendicular to the axis of revolution. And then that's going to tell me I need to integrate this thing with respect to y. Bounds in terms of y, function in terms of y. Okay. Does that all make sense? That's how I would recommend to you that you do all of these problems, at least until you kind of get a feel for them. Okay. So everything in terms of y. So then, where would y range from? What would our bounds of our integral be in terms of y?
0 to 6.
0 to 6, right? 0 to 6. Y goes from 0 to 6. Okay, then we need to compute the outer radius and square it, and the inner radius and square it. So what would our, let's do this. What would our outer radius be?
Y squared.
X, y squared?
Yes.
Y, x or y squared?
Y squared.
It's got to be in terms of y, right? Remember the outer radius, we're revolving it around the y-axis. So our outer radius is going to be determined by this distance from this to this. An outer function to the axis of revolution. That's our capital R, outer radius. Again, right minus the left, the right function is y or x, minus the left function, which is 0. That's not a great color. I guess it's darker. Yeah, that's okay, so that's going to be y squared. That's our outer radius squared minus our inner radius squared. What's our inner radius? Yeah, it's this thing here. Right minus the left. The right is again 2x. We need that in terms of y though, so we need it as x equals 2. So the right is y over 2 minus the left again is 0. Y over 2 minus 0. Inner radius squared. And then of course, with respect to y. Okay, so that's our setup for the volume. Anyone have any questions? So again, it's just powers of y, 54 pi. All right, I think we have one more example here. A lot of times, as we've seen, when you can use symmetry, it does make it easier in the sense that one of your bounds is typically, depending on the symmetry, but for the most part, one of the bounds is usually 0. It's always easier to evaluate that. In an instance where we have like absolute value involved, I think it's absolutely easier to use symmetry. And then our last section, when we get to chapter 12, and start looking at integrals and derivatives in polar coordinates, Symmetry is like super efficient as well. So something that shouldn't be overlooked. So we're just going to draw this graph best we can. Okay, so we have the, yes, thank you. We have the absolute value of x. Doesn't want that. Blue, please. I'm just going to draw absolute value of x. 2 minus x squared, what does that look like?
Downward facing parabola.
Yeah, it's a parabola opening down. Where's its vertex?
Instead of 2, 0, 2.
0, 2, yeah. I'll do this in red. So I don't know, we'll just say this is 2. Opening down. Okay, and that's it. And it says use the washer method to find the volume of the solid. Generated washer method revolved about the x-axis. Will revolve around the x-axis. In order to generate a washer, our slices or rectangles have to be perpendicular to the axis of revolution. So here's our rectangles. They have a thickness x direction, dx. So notice my crummy drawing doesn't do it justice, but there is symmetry here. You can either use that symmetry or you can compute 2 different integrals, right? So let me just graph it a little better here. So there's, a better representation of what we're dealing with. If you're just gonna use as it is, then we've got to do a couple of things. Once we have our kind of picture established, we're calculating the volume, taking this and revolving it around the x-axis. So what do we need to know from here?
That endpoint,
This endpoint,
no, the one where they cross.
this one right here. Right, we need to know what this point is. And if you're not going to use symmetry, you also need to know what this point is as well. So what are those 2 points of intersection? Or what is that single point of intersection?
-1, 1.
Yeah. It was -1? -1 and 1?
Yep, if you compute them both.
Yeah. Do y'all agree? So remember I guess the downside with dealing with the absolute value is there's always like 2 pieces to it, right? One of them is x when x is larger than or equal to 0, and the other one is negative x. Right, so that's always the difficult thing with absolute values to deal with. So, instead of trying to figure out both of these intersection points, we'd say, all right, well, where does negative x intersect my quadratic, and where does positive x intersect my quadratic? We can just look at it. We can just look at it like this and double the volume, right? So let's calculate this volume and just double it. Does that make sense? That way we don't have to deal with the negative x part with 2 different definitions, depending on where we're at. Okay, so the volume then would look like what? Anybody want to take a shot at it?
an integral from 0 to 1.
Right, 2 pi, remember the 2 comes from the fact that we're doubling that volume. The pi is always in the disk washer formula. Okay, integral from, sorry, 0 to 1. Okay, then we have to find our outer radius minus our inner radius. So what's our outer radius?
X squared plus 2.
X squared plus 2.
I think it's negative.
Negative x squared plus 2?
Yeah.
Oh,
I
okay,
just
yeah,
flipped
yeah.
it around.
I gotcha. Right, so the distance from the top function to the axis of revolution, right? That's our capital R outer radius. So there's our outer radius. We have to square that minus,
The other one, which is absolute value of x squared.
which is the absolute value of x squared, right, for little r. But is it really the absolute value of x squared?
No, because if it's squared, you still get both.
You still get both. And because we just chose to look at that part on the right side, where it's larger than 0, it's just x, right? So yeah, it's just x squared. Absolute value of x squared is also x squared, so how do we do that? Do this. Okay, what do y'all think? Does that look all right? Okay, so that's our setup. Does anyone have any questions on that? So definitely the easier route to take. The other one we would have to do 2. You have to do 2 integrals. So the first one it would be pi integral from -1 to 0, and the outer radius was still 2 minus x squared, minus the inner radius would be negative x squared. So that would give us the region to the left if we did take that into consideration. And then we have plus the integral from 0 to 1 pi times that of what we have. Right? So you see, you actually just have 2 of those. It's the same thing. But this is with both pieces considered. All right. I'm just going to, again, write the answer down. They're just powers of x, so I don't want to spend a lot of time doing these things. Sort of tedious, but 76 pi over 15 for that one. So that's the idea for disk and shell methods. 6.3. Also have the general slicing method in 6.3. Anyone have any questions on 6.3? 6.3. So, yeah, let's take a break and then we'll start a new section. Okay, the idea extends to 6.4. They're going to call this the shell method. And so this is what happens when we slice parallel to the axis of revolution instead of perpendicular to the axis of revolution. So when we revolve this thing parallel, we're revolving this around the y-axis. There's one of our slices. What we're creating is, similar to that of a disc, but you've got to imagine that thickness isn't there. So really this takes on the form of a cylinder. And so the area, the formula rather, for this volume is derived off of the area of that cylinder. So they're cylindrical shells. They just refer to them as a shell. They are cylindrical shells. And let's go here. You can sort of see the formula right there. But the idea is that we need to compute the area of each one of these things. So let's just call this dimension h. That's just the height of each cylindrical shell, and we need the area. So we need a linear dimension times a linear dimension, and so the other linear dimension is just the circumference of the circle, which is 2 pi r. So this volume is just 2 pi r times h. And keeping in mind, like our axis of revolution would be here. We'll look up here at this region here. And so, you know, it's really this rectangle that we want to pay attention to. Here. That's kind of the cross section of our, we're cutting our cylinder in half. How would we define the radius? The radius would be what here? Neither. What's the radius of this cylinder? So like here's our, just imagine that's our cross section right there. The radius of that is the distance from each cross section to the axis of revolution, right? So that's our radius. That's our radius. And the height, of course, is just the height of this thing right here. This is h. So again, h is measured top minus bottom, function minus 0. Radius is measured as right minus left. And so the radius also varies, right? Depending on where we're at, we could have a radius here. If we did a cross section right there, then our radius, of course, is now this. So we'll just label that radius 1, radius 2, I guess. But the idea in this situation is that the distance, the right minus the left, this value minus 0, that's just some x value. Like if I told you that this x value were 5, then we would know that radius is 5. That's kind of hard to see. It's like if we knew that x value was 5, we know that the radius of that particular cylinder is 5. If we know this x value, we know the radius of R1. So we're just going to label the radius as some measurement in the x direction. We're just going to call that x itself. So that's where this x comes from. Just write this out a little bit larger, I guess. This volume is integral from a to b 2 pi times the radius times the height, which is given by f of x. So there's our 2 pi r times h. We got this is our formula when we're finding volumes when we slice parallel to the axis of revolution. So there's parallel slices and perpendicular slices. I always just remember that the shells are parallel, just because it kind of rhymes.
In the previous washer method,
Mhm.
the radius was f of x,
Yeah, one of the radii were f of x.
and then in this one it's the
Height, right? So that's why I think it's like super helpful to draw your pictures out. If you're trying to if you're just given some stuff and you're trying to visualize that in your head, chances are for most of you, you're gonna mess up somewhere. But does everyone see that? The height here is just because the height of each cross section is like this. We always measure that from top to bottom. So if we go back to our discs or our washers, washer. Somebody was like, "Hey, are you from the South?" And I'm like, "Yeah, how'd you know?" And they say, "You say washer." I think that's the only, the last remnant of my southernness is that word. So the idea is the same. The radius is this distance still in this situation. So it's still top minus bottom. We're just dealing with a different figure here, where that's not the radius anymore. That's just the height of each shell. So that's why I think it's more important to recognize how you're setting things up. Is the radius running like this? Is the height running like that? That way you know for sure, hey, the height's the top minus the bottom, or right minus left, or whatever it is. So yeah, that's what we're dealing with. Anybody have any other questions or comments? So both methods give us the volume of revolution. Again, we've got two different methods because we've seen certain functions you may or may not be able to solve for one of the variables, right? Like I could take a function and solve for x or y, linear, quadratic, but things to the third, fourth, fifth, sixth power, etc. Pretty impossible to solve for x or y if that's the case. Or if you could think of trig functions, solving for them, you would involve an inverse trig function. Those are difficult to integrate sometimes too. So two methods to determine the same thing, which is a volume of revolution. It's just which method do you use generally depends on, do I want to integrate this thing with respect to x or with respect to y? Which one's easier? So we've got two different methods. That makes sense? So I could take a region like this and say, to me that looks easier to make slices like this and integrate with respect to x, right? So, in that instance, let's say we want the volume revolved around the x-axis, then clearly integrating with respect to x is easier. If I'm already revolving it around the x-axis, now my slices are perpendicular to my axis of revolution, so the disk method or the washer method is the easiest thing to do here. If I tried to do this, if I'm revolving the same region around the y-axis, and I do this, again, this thing was easier to integrate with respect to x. I'm revolving it around the y-axis. Now I'm using the shells instead of the disk washer. So let's just pretend those two functions, where it's impossible to solve one or both for x. We couldn't solve it for x. Okay. So we will look at an example where we use both. You do see that it does give you the same volume. So case in point, y equals cosine of x squared. This is cosine of x squared, not cosine squared. Cosine of x squared. Y equals 0. for x in between 0 and root pi over 2, excuse me, use the shell method for the volume revolved about the y-axis. So, oh yeah, we're gonna do the whole thing. So this is root pi over 2, and we can graph this. I wouldn't necessarily expect y'all to graph that on the exam, but it does look like this. That's why. Just write this out. This is why. All right, so like, let's say we wanted to find this volume. We're rotating this thing around the y-axis. If we tried to say, all right, well, I want my, let's pretend that we don't have any instructions, it just says find the volume. If I were to come in here and say, all right, well, I'm going to slice it this way, perpendicular to the axis of revolution. If I'm doing this, then I'm using the disk method, right? My slices dy are perpendicular to the axis of revolution. But what that would mean is that I need cosine of x squared equals to y. I would need to have that thing solved for x and be able to integrate that. So here, here's, I guess, initially we could see, we might just want to stop here and say, I don't want to finish solving that for x. It's going to be too difficult to integrate, right? Do I want to integrate this? I don't know, maybe you do, I don't. Looks really difficult. So then I would say, all right, well, I don't want this situation. I don't want the disks involved in this situation in any way. Yeah? So I'm just going to back up. I know it explicitly tells us to use the shell method revolved around the y-axis, but again, just to illustrate the point on why we have two different methods. Okay, so shells are parallel to the axis of revolution, which is our y-axis. Our slices are running like this. We're integrating with respect to x. Just draw this out again. Here's this. So we're revolving around this axis here. That means this thing is going to get revolved over here and look like this. Right? There's that cylinder. Here's the radius, the distance from here to here, and here's the height. So cylindrical shells area pi r, 2 pi r times h. We've got 2 pi times r, and this radius here is just some x value. All of our radii are just an x value. So x times the height. The height is again measured as top minus bottom function minus 0. Pi times r times h. The bounds are from where to where? X ranges from 0 to pi over 2. space. Fail. I'm just gonna leave it. Okay. So there's our setup. Does anyone have any questions on that? Okay, so how do we integrate this? Yeah, use substitution. It's all the only technique we have right now. It's not a known antiderivative, so the only other avenue we have is use substitution. Let's see if we can fit this here. So what are we gonna let u equal?
X squared.
Yeah, x squared, because it's a constant times its derivative is setting out as the x. So u is x squared, du is 2x dx, or 1/2 du is x dx. So we've got our 2 pi integral. We're going to put in a 1/2 and a du for the x and the dx, and then this is just a cosine of u. So remember, you can find the antiderivative here, then convert back to x and use the original bounds. Generally, it's just easier to change the bounds because your u substituted integral will always be easier than the original one you started with. That's the whole point of substitution. So if x is 0, then u is x squared, 0 squared is 0. So I'll just draw this in red. This is our u value at 0. If x is the square root of pi over 2, then u is just pi over 2. All right, so we've run out of space. But we've got a pi out front. We've got the antiderivative turns into sine evaluated from 0 to pi over 2. Does anyone have any questions on this?
What's the answer on that one?
The answer is pi. There's nothing wrong. I still see people translating the antiderivative back in terms of x and evaluating it from 0 to root pi over 2. There's nothing wrong with that. It's always just a little more involved. So, you know, whichever route you prefer, I don't have a preference in how I would rather see that. Any other questions on this?
What happened to the yellow X?
So that yellow X got turned into this right here.
Oh yeah, the 2X.
Yeah.
And then you saw.
Yeah. Any other questions? All right, so we've got a region bound by the functions given. Again, use the shell method and revolve it around the x-axis. So I'm just going to draw this region. It's always sketch the region and then go back to which method you're using so you can determine which way your slices are running, which determines how you're going to integrate it with respect to what variable. 0 and 4, so we have the square root function. Y equals to 0 there, and x equals to 4 there. So just again, make sure that the region you're working with in your drawings or your sketches or whatever is bound by all 3 or 4 or whatever you're given. So we're doing this region here. So that we've sketched our region, shell method. We're revolving it around the x-axis. So our shells need to be parallel to the axis of revolution, or rectangles, or whatever you want to call it. We're integrating this with respect to y. So when we integrate with respect to y, of course, the bounds need to be in terms of y, and our functions need to be solved for x. So we've got to take y equals root x. We want that as x equals. So what's our radius here of the shell?
Y minus 0.
Y minus 0?
Which is
Do y'all agree? Let's draw this region here. Sort of visualize it a bit further. Oops. Oops. Make sure you draw it right. So we're taking this thing and we're revolving it around the x-axis. So I'm just going to focus on our rectangle here. This is going to be revolved here. Other part of that circle. There's this part of that circle. So the radius of that cylinder from axis of revolution to the rectangle or cross section itself, right? That's the radius. Okay. The height is this distance, the actual height of the cross section. It's our h. It's just sideways now. Is everybody cool with that?
So height is x.
So yeah, so what is the height? How do we measure that distance?
The right minus the left.
It's the right minus the left. It never changes. What's the right? 4,
I think.
right? 4 minus
Y squared.
y squared.
Oh.
Height, let's write it here. H is 4 minus y squared. Right minus the left. Is everybody okay with that? So I know these pictures can get confusing, but initially how we set this up, and then based on the revolution, to measure most of these things, it's always right minus left or top minus bottom, depending on how they're running. That will take care of 90% of what you're trying to establish with these. Now, we've sort of switched roles here. R would be defined as what? That distance. Top minus bottom.
The y value.
The y value, right? Like this is my radius. Whatever this value is, that's R for that cross section. For this cross section, that distance is whatever this y value is here. So our radius is just y. Are there any questions on that? Okay, so then we're going to say our volume is 2 pi times r times h dy. And y ranges from where to where?
0 to
0 to 2.
0 to something, right? Remember, this is an x value of 4. plugging that into the square root function. Square root of 4 is 2. 0 to 2. So there's 2 pi times our radius times our height for the shells. Again, you distribute that out, you've got powers of y's to integrate from 0 to 2 times your 2 pi. Any questions on the setup?
Eight pi is the answer.
So please, on the exam, just show a little bit more than that. I don't expect you to deal with all the tedious arithmetic by hand, but you wanna take it out like this at least to get points. If you write it out, just find the antiderivative. Again, all of this, the rest of this stuff from this point is just arithmetic. Okay. So if on the exam you write this and then this and then this and then your answer, like I think that's probably as little as you could get away without me saying, well, how did you go from here to here? Does that make sense? Is that clear? And if you have questions like, hey, did I show enough work? Just please ask. It's better to know whether you're showing enough work or too little work than it is to not know. Yeah.
So are you against us using the integral calculator on our calculators? Like if we write all that, we get to that point, and then we...
Yeah. I kind of am.
You are?
Yeah.
Okay, cool.
Yeah, because we could just type this into our calculator and it's going to say, hey, it's 8 pi. Nice, we're done. Which is fine for some of you, but I know others, it's been a while since you've taken calc. You might not remember some of this stuff, especially like the last one where it was x cosine x squared. If you just write the answer was whatever pi or whatever it was, there's some gaps there that you need to fill in, right? So don't rely on your calculator. I want to know what you can do, not what your calculator can do. This is a calc class, so I'm not grading you specifically on arithmetic. Like, to me, that's secondary. Setting this stuff up, showing me how you would integrate it is pretty primary. Yeah, I hope that's clear. If it's not, then just ask me during the exam. Okay. So these were just sort of things we're going to skip. I guess let me just write some things here in case you want to take these 2 pages out. So the area of our cross sections are 2 pi r times h. And a couple of key things here. Shells are parallel to the axis of revolutions. Axis of revolution. We'll say h is equal to maybe 1, the right minus the left, in the sense of dy. You're integrating with respect to y, that's our heights will be determined that way, or top minus bottom, in the sense that you're integrating with respect to x. I hesitate to put like what the radius is, because sometimes that changes depending on what you're revolving the region around. But in this case, most of the time, if it's that y-axis, your radius is just y. Here, your radius is x. But it really does depend on the axis you're revolving around. Okay, our discs, as we said, disc or washers. Discs are perpendicular to the axis of revolution. Same thing here. This is
think about pi r squared, pi times your function squared, or pi times your outer function squared minus your inner, pi times your inner function squared.
I mean, I guess we could say more stuff, but. So those. The next example is going to show us that both methods do give us the same result. And again, it's always nice to have choices. One might not be doable, but the other one is. So here, of course, this example will be doable using both methods. We just want to kind of look at it, and maybe it'll help iron out the differences too. So we have the region bound by y equals x and x to the 1/3 in the first quadrant. So does anyone remember what x to the 1/3 looks like? Yeah. It's like, if you remember what x cubed looks like, it's like a sideways x cubed. So it's like this.
X to the 1/3 looks like this.
Kind of looks like that. So we'll do this.
Are
X
you
to
gonna
the
have a
1/3.
list of
Huh?
Are you gonna have a list of what we should know how to graph versus what we don't need to really know how to graph by hand?
Probably not. I mean, you should like know how to graph most like basic functions.
Okay.
If they're like funky arguments like cosine of x squared, then I would have that graph for you. But yeah, most of these algebraic functions and trig functions, you should know what they look like. Okay, so x to the 1/3, y equals to x. I'll just label this. Here's y equals to x. In the first quadrant, so it's that region there, revolved about the x-axis. Revolving that around the x-axis. And in this one, example 3, we want to use the shell method to find the volume. So if we're revolving that region around the x-axis using a shell, our shells have to be parallel to the axis of revolution, which then indicates to us that we have to integrate with respect to y here. So we've got this thickness here, dy. Which again, we need our function solved for x. One of them already is. We need y equals x to the 1/3. We need to solve that for x. We can integrate that. So I guess now the question becomes, we're using shells, which are 2 pi times r times h. So what's the height of our shell here? Anybody else? What were you saying, Alice?
The y
Yeah, the h. What is our height here? What's the height of each one of our shells? Do you wanna?
the top minus the bottom, so the y cubed minus y.
Okay, so careful here. Remember, it's running this way, right? That's the height of our rectangle is the height of each cylinder. So it's running that way. It's the right minus the left. Yeah. So right function is x equals y. So y minus y cubed. Right minus left. What's the radius? Okay, good. The radius is y. Again, we're imagining that this shell is getting revolved around this axis. So that's our radius. Top minus bottom, y minus 0. Oops, let me write it this way. Top minus bottom, which is y minus 0. Okay, so then our volume here will write. And we're basing it off of our shell, 2 pi times r times h. 2 pi times r times h dy. And then y ranges from where to where? So 0 to, what is this y value? Is it 1? Again, if you're not sure, then you've got to equate these things. When does x equal x to the 1/3? Or when does y equal y cubed? 0 and 1. So that's kind of like what we did in 6.2. We find the points of intersection. It doesn't matter which one you solve for, even though we're integrating with respect to y, all we're trying to do is find that coordinate, right? We're just trying to find the y coordinate. If you know where they intersect in terms of x, then you can just plug that back into the relations and get the y value. Okay, so there's the setup for the volume. Does anyone have any questions?
Yeah, how did you get the radius again? I
So-
know top minus bottom, but I guess what I did was I took the top function minus the bottom function.
Okay, yeah, so for the radius, you wouldn't do the top function minus the bottom function because we're explicitly talking about what's the radius of that specific cylinder. So
Oh, that's
right, we're only focusing on the cylinder, not just like when we looked at disk and washers, we were focusing on the distance, sort of this linear distance, either this way or this way.
Gotcha.
Yeah. Is everyone clear on that? We don't care, like, this isn't the radius, right? Like, that's not the radius. 'Cause what we're talking about is 2 pi RH. That's the radius of the cylinder. The cylinder is generated when we take this slice and we revolve it around this way, right? So what is the radius of that cylinder? Okay, any other questions? Again, if you have to, just draw the whole thing out. You know, you're drawing the region already. You're drawing this region already. It might be conducive to draw it out completely. So we're just focusing on that rectangle, revolving it around this axis. So what we're gonna, if you could try to draw this, I don't know, sometimes it's not so friendly, but. This is gonna be here, here. So we have this sort of, I don't know, this sort of bowl shape. That's terrible. We have this gradual curve and this gradual curve here. So something like that is what we're trying to find the volume of. Here's our axis we revolved it around. Here's the rectangle we were focusing on. When we revolve this thing around, we get this thing, right? And so we're saying, all right, well, just turn it around and look at it like this, because those are all what we're generating anyways. But here's the radius. It's this distance from the axis of revolution to the rectangle itself. So that's our radius, right? I don't know if that's any more helpful than it was, but for whatever it's worth. There you have it. Okay, so this is our volume. And that's 4 pi over 15. Again, just power rule involved here, that's it. Any questions on that? So now I want you to try this exact same thing, but we're gonna revolve around the x-axis. Using the disc or washer method, depending on which one it is.
At one point, wouldn't it be a disc at the 0 point?
Yeah,
And then it becomes a washer?
yeah, but it's pretty much a washer throughout, right? Just because it's at that one point. When you revolve that point around itself,
It's like nothing.
yeah, you don't get anything, so, right? So I'll just go ahead and redraw the region. Y'all can work on this.
Someone stole mine on the first day of physics last semester, so I was like, screw this, I'll paint it. If you walk away with it, I see it shiny.
They still have dirt on this.
Yeah, I walked away and I came back and it was gone. On tests, do you usually ask for a certain method, or are some of them like, you decide which method to
Yeah,
use?
it'll say like this one does, or it says, you decide.
Okay.
But most of them should specify, just so that I can see you're setting it up. Otherwise, somebody would tend to gravitate towards one method, and just use that one. So yeah, it'll say different ones. Okay, I don't really see anybody writing anymore, so I'm just gonna use that as either you've checked out or you're done. It's either way. So the it specifically says the disc washer method revolved around the x-axis. So the disc and washers are perpendicular to the axis of revolution. We're integrating this with respect to x. So it's going to be, we've got a gap between our function and the axis of revolution. We're going to have an outer radius and an inner radius here. So let's write this out. It's pi times the outer radius squared minus the inner radius, pi times the inner radius squared. So our dx, x goes from 0 to 1, down 0 to 1. We have this time we're thinking about this thing, right? We have to figure out the outer radius here, which is this distance. That's our capital R, and our inner radius, which is this distance. Yeah? Okay. So that's it. Our top minus bottom. That's our x to the 1/3. So there's the outer radius. Well, let me do it in the same color. There's our outer radius. We need to square that. And our inner radius is top minus bottom, x minus 0. Just x. So that's our setup. Anybody have any questions on the setup? So we'll just verify that this is the same as what we have above. Just powers of x again. Antiderivative, we've got x to the 5/3 times 3/5 minus 1/3 x cubed from 0 to 1. And that's going to give us pi. We'll just write all this out. X is 1. Minus x is 0. So we have 3/5 minus 1/3 times pi gives us the same result. So same volume, different methods. And a couple people have asked on the exam. It'll say use this method to find the volume, or it could be one like this where you could do it either way, and it would just say, just pick whichever method you want, something like that. But most of them will specify a specific method to use. Do y'all have any questions here? All right, we might come back to this one here on Thursday, but this is kind of like a question on your homework, and I just want to give you a chance to think about it a little bit before we just do it. I mean, a lot of these are similar to homework problems, but we'll come back to this one on Thursday. We'll have to come back to something on Thursday, so we're just going to come back to this one and start with example 6 here on this page, because this one's actually revolved around a different axis. All the ones we've seen have been revolved around the x or the y axis. So we're going to revolve this region about x equals to -2 using the shell method. So again, we're just going to draw out real quick what this looks like. X squared, x equals to 1. Where do we want to look at? Let's just say it's here. And y equals to 0. We don't really need that part. There's our region. We're going to revolve that about x equals to -2. Let me just extend this a little bit more so it's somewhat close.
Can't see.
So we're going to take that region, we're revolving it around, I probably should have left even more space, but we're going to revolve it around this axis here. Okay, so shell method, axis of revolution, shells are parallel to our axis of revolution. Our shells are running like this, integrating with respect to x. So that rectangle I've drawn here for my shell, whether I draw it this way or this way, if I revolved around another axis, right? That's what you draw there for the shell is always the height of the shell. The radius, again, will always be the distance from your cross-section to the axis of revolution. So that's our radius in this case. Our height is just this here, this dimension here. Here to here. That's h. Does that make sense? It's always going to be the case with shells. So we're just measuring the height, top minus bottom. Unfortunately, again, that doesn't change for us. The top function is always x squared, the bottom function is always 0. X squared. So what's the radius?
X minus -2.
Our claim is the radius was x minus -2. What do y'all think? Is that our radius? Right minus the left. Again, this is just some x coordinate here. This is x minus the right is -2. X minus -2. That's x plus 2. Does that make sense? I mean, you might want to just draw the whole thing out if it doesn't. Here's our region. We're revolving it around this. Here's our rectangle. It turns into this this shell over here. So that's the radius of your cylinder. Any questions? So the height of the shells didn't change because we're revolving it around a different axis. But what changes is the radius. So our volume. Remember, you just reminding ourselves that we're dealing with the shell method. 2 pi RH. 2 pi RH down here. 2 pi R H. That's right. Yeah, 2 pi times R times H. And then X ranges from 0 to an X value of 1. So our bound's 0 to 1. And that's the setup for number 6. Anyone have any questions on that? So here we would just distribute x squared into that. We've got powers of x once again. As we've mentioned, there's not a lot of integration techniques at this point. So we're somewhat limited in what we can do here. We can certainly illustrate the main idea of these volumes of revolution. After we look at different methods for integration, we could revisit some of these with more like elaborate functions where we are able to integrate inverse trig functions, or we are able to integrate logarithm, natural logarithms, something like that. So yeah, 11 pi over 6 is the answer. Is everybody okay with this? Questions? All right. So you're probably going to have a problem similar to your homework as 6 or 7, but you might want to try number 7. We'll look at it next class. You should get the answer to be 17 over 15 times pi. And we'll look at this one and the one we skipped, example 5, on Thursday. Does anyone have any questions before we take off? All right. So I will see y'all Thursday.